Okay, so now we know how to identify something will have an inverse function. We need to talk about how we're going to find the formulas for those inverse functions. So I kind of gave you a hint at it earlier, but if a function is one-to-one, a formula for its inverse can generally be found as follows. We are going to replace fx with y. Then we're going to exchange x and y, and then we're just going to solve for y. So like I said, generally this is how we can do it. Sometimes you get some really complicated inverses, but for the most part, this is how we're going to do it. And then after we do that, we replace our y with f inverse of x. So as an example, we want to determine whether this function 2x minus 3 is one-to-one. So I'll make like a quick sketch of what it should look like. Oops. So as we can see, we know it's going to have an intercept here at -3. It's got a positive slope, should be increasing. It's basically a linear equation. It's going to look like this. Actually, it's even steeper than that. Looks like this, maybe. So what we see is this is going to pass horizontal line test. That means that it is one-to-one. That means there is an inverse. So what we have here is that we have fx equals 2x minus 3. So our first step is to replace fx with y. So what we're doing here is we're essentially swapping the domain and range. Domain's my x's, y's my ranges. So now y is going to be x and x is going to be y. Now we're just going to solve for y. So just to point out, at this step is when we actually have our inverse function. We're just going to complete it so we can just write it as f inverse. So if I want to solve for y, first thing I'm doing is going to add 3 to both sides. So I have x plus 3 equals 2y. Then I'm divide both sides by 2. I'll put this over here. That means y will be equal to x plus 3 over 2. Or you could say it's 1/2 x plus 2 over 3, one or the other. It's the same thing. But what's important is that we were trying to write it as a inverse function. So now we replace that y with my f inverse of x. So this is the original function, and then this is its inverse function. And also just to point out, f is the inverse of f inverse as well. So these are inverses of each other. And just to show you, if we were to graph these together, like we said, our original in the green was this linear equation. And what we're going to see is that it is essentially going to reflect over y equals x. And that is my inverse function, is that reflection of it. So we see like this point here has now reflected to this point right here. So as we said before, the function is just the graph of the function's reflection. The inverse function is a reflection of the original function over y equals x. Okay, so number 5, I've given you 4 functions. or 4 functions. So first you need to determine whether they're one-to-one, and then if they are, what their formulas will be. So one of them, I'll tell you, is not one-to-one. And some of these find the formulas maybe a little difficult, which is why they're here, so we can talk about how we're going to do that. All right. So I'm going to do this like this. So we're going to focus at one function at a time. So this first one, if you do sort of a quick graph of it again. So if you did a quick sketch of this, what you're going to see is that this is very similar to the last one that we had. It's going to be a linear equation. So it means it's going to cross somewhere down here at -3 and look like this. So as we see, this one's just increasing everywhere, or you could say it passes its horizontal line test. This is a one-to-one function. So that means I can find an inverse. So like we said, first step is we replace our function notation with a y. Then we switch our x's with our y's. And as I said, this is technically right here when I have my inverse function. We're going to keep going with it and solve for y. So add 3 to both sides, then divide by 4. We are going to, oops, sorry, this is my y. I can fix that. We see is that y is going to now equal x plus 3 divided by 4. And then we just replace y with my f inverse of x. So f inverse is just x plus 3 over 4. All right, so b, this is a rational function. And what we see here is, like, this was -2. That's going to be an asymptote. Also, the x-axis acts as an asymptote. And we have something that's going to look like this. So what's important here, I'm not going to cross this asymptote or this one. So what we see here is essentially this keeps decreasing here, keeps decreasing. What's important here is it's passing that horizontal line test. Right. Sorry, my horizontal lines are not staying very straight. I'll have nothing here. I just skip everything. But as you see, I only ever cross once. So once again, we have a one-to-one function. So we are going to take my function notation, this g of x, and replace it with y. And then now my x's are going to become y's and my y's are going to become x's. So we have my inverse right here. So at this point, you might be asking yourself, how am I going to solve for y? So here's a little trick. If your y happens to be in the denominator, so this is x plus 2, just multiply both sides by that whole denominator. What's going to happen is that this will cancel with this, just like if it was 3 down there and we multiplied by, or sorry, if it was 5 down there and we multiplied by 5 to get rid of it, get rid of your denominators, same idea. So what you're going to be left with is over on this side, as I'm going to have y plus 2 times x, and because these eliminated, we're just left with that 3 there. So what we can do is we can multiply this, so this x can distribute. So we're going to have xy plus 2x equals 3. So you might be thinking this is getting more complicated. It really isn't. Like I said, as I would need to do that, I need to get at that y. There's a few other ways you could have done this, but we need to get at that y. So what I have is an xy here. I want to isolate it. So first thing I'm going to do is subtract that negative 2x. Give myself a little extra room here. And then you'll have xy is just going to be 3 minus 2x. Now I just need to get rid of this other x. So I'm going to just divide by it. So we get y is equal to 3 minus 2x over x, which then we could just write as, oh, we had g originally. So instead of saying f inverse, we're going to say g inverse is going to be equal to 3 minus 2x over x. You may have, if you also, another thing you may have gotten trying to do this, if you did it a little differently, is you can end up with 3x minus 2 as well. That is another version of this as an equivalent equation, but like I said, that's another possibility had you done this a little differently. So if you were to graph this function, so C here, as another rational function, we actually have a vertical asymptote at about 1/3, or sorry, horizontal asymptote at about 1/3. And we have a also at about 1/3 again. We're going to have your vertical asymptote. And it's going to look like this again. Second, I'm trying to get that. It's just not smoothing out. No, going too far. There we go, like this. But just like we saw with B, this is passing my horizontal line test. This is a 1-to-1 function. And because it's a 1-to-1 function, I can actually look for an inverse. So we have h of x is going to be plus 3 over 3x minus 1. And we replace the function notation with a y. So remember, we need to change my x's to y's and my y's to x's. So this y is going to become x now, and both of these x's become a y. So if you have multiple x's, they all become y. Okay, so technically that's my inverse. So I'm going to do like I did before. I don't like this y in the denominator because I want to solve for it. So I'm going to multiply both sides by 3 my y plus 1. So that's going to cancel out that denominator. And I'm going to have x3, sorry, that's a y. That's the hard part, is you keep messing up and accidentally writing your y's and x's in the wrong place. Okay. So we have x3 is and 3y plus 1 multiplied to one side. This cancels, leaving me with y plus 3. So I want to make sure all my y's are left alone on one side. So I'm going to do like we always say when we're trying to solve an equation for a particular variable. Try to distribute and simplify as much as you can first. So I'm going to distribute that x. I have 3xy plus x now equals y plus 3. So I'm going to put my y's to one side. So to do that, It doesn't matter which one I do, but I'm gonna just subtract this y to get it over 3 here. Then anything without a y, I want on the other side. So I'm going to subtract x from both sides. So now that I did that, what I see here is that I have a y and a y. So we're just going to do some factoring. I can factor a y out of both of those. So if I do, that's going to leave me with 3x minus 1. And then I'm just going to divide both sides by 3x minus 1. And what we're going to end up with, which I'll write up here, that will cancel. Y is going to be equal to 3 minus x over 3x minus 1. Which then we can change. So this original function was h. We're going to change this to h inverse is equal to 3 minus x over 3x minus 1. Sorry about that. Let me go back and reduce some of that a little bit. So I accidentally changed this to a plus. So what I should have done is multiply both sides by 3, where I want 3y minus 1. And then we would have had x, 3y minus 1 over y plus 3. Distribute that to x. So we have 3xy minus x equals y plus 3. We're going to subtract y from both sides, so I get my y's all in one place. 3xy minus y minus x equals 3. Then I'm going to add that x, because I want to just have things with terms with y on one side and all my terms without y on the other side. So I can do this factoring here in a moment. So this is x plus 3. If I pull out y, I'm going to be left with 3x minus 1, x plus 3. Divide both sides by 3x minus 1. It's going to leave me with y is just going to be x plus 3, 3x minus 1. So h inverse is going to be x plus 3 over 3x minus 1. So that looks right, because what this should have here is that this is one of these cases that occasionally happens. The function is actually the inverse of itself. So this is what we have here. So we go through and we find the inverse, and it just happens to be the same function as its own inverse. All right, so probably without graphing this, maybe you're catching on the pattern that I got an x squared, which seems to be a problem over and over again. So if I was to make a rough sketch of this graph, second, it's about, here you have your vertex. So this is a quadratic. And what we notice is that it does not pass the horizontal line test. So this is not 1-to-1, meaning we have no inverse function. If we want an inverse function, what we would have to do is, we'll see this in a bit, but we would have to restrict our domain, meaning I would have to like cut off half my function, because you see that remaining half would actually be something that it's 1-to-1 that would have an inverse.